Welcome you all to Principles of Organic Synthesis. Presently we study electrophilic aromatic substitution. In this topic we have studied so far the principles of electrophilic aromatic substitution and Pirelli-Crafts reactions. In this lecture we will study the formulation and the related reactions. This slide shows the Caterman-Koch formulation. The reaction involves, as you can see here, the benzene ring undergoes reaction with the carbon monoxide, the presence of hydrochloric acid and aluminum chloride to give benzaldehyde. This reaction usually is carried out under high pressure. Alternatively, you can also use copper chloride. As you can see, the copper chloride helps to undergo reaction of the carbon monoxide with hydrochloric acid to form the acylium cation. Once you form the acylium cation, which is the electrophile in this reaction, which undergoes reaction with the benzene ring as shown, and you will be able to have this intermediate carbocation. You have this one, removal of proton can give benzaldehyde as a product. So, here are some of the examples shown. You can see here the reaction of isopropyl benzene with carbon monoxide in the presence of aluminum chloride, hydrochloric acid, copper 2 chloride given to give this corresponding aldehyde as a product. Here the reaction of paraxylene with carbon monoxide in the presence of hydrochloric acid and aluminum chloride is shown to give this aldehyde as the product. So, this reaction has some limitations. For example, if you have functional group like amino group and phenol and ether and nitro group, the reaction does not work. This because when you have the amino group and hydroxy group, they can make chelation with your Lewis acid. This similarly, if you have ether, that also can make chelation with Lewis acid, and the reaction can be slowed. Similarly, if in the case of nitrobenzene and this aromatic ring is electron poor, in other words, when you have the electron withdrawing group, the nucleosphilicidity of the benzene ring is considerably reduced. Therefore, is not sufficient enough to undergo reaction with acylium ion to give this benzaldehyde as a product. In summary, as you can see here, in Caterman-Koch formulation, benzene can be converted into benzaldehyde using carbon monoxide in the presence of hydrochloric acid and Lewis acid like aluminum chloride in the presence of copper 2 chloride with moderate good yields. They have some limitations. If substrate like if you have the functional group like amino and ether and hydroxy group, they do not work. And similarly, if you have strong electron withdrawing group like nitro group, the reaction also is not effective. However, you can carry out the reaction with alkyl benzenes. They can readily undergo formulation to give the corresponding aldehyde as the product. Just we have seen the Caterman-Koch reaction, where you use the combination of carbon monoxide, hydrochloric acid and Lewis acid for the formulation reaction. In place of carbon monoxide, you can also use hydrogen cyanide. This is known as Caterman formulation, and here the reaction condition shown, instead of hydrogen cyanide, since it is toxic, what you can do, you can start with zinc cyanide and hydrochloric acid, and you can readily do the formulation. An example shown here, the mescaline can be converted into the corresponding aldehyde in good yield. The reaction mechanism shown here, in this case the zinc cyanide first undergoes reaction with hydrochloric acid to give hydrogen cyanide and zinc chloride. Once you form this one, the hydrogen cyanide undergoes further reaction with hydrochloric acid to give this cation intermediate, which acts as the electrophile in this reaction. Once you form this one, now this benzene ring is nucleophilic, which can undergo reaction with this cation intermediate, and then you can get this cation. Once you form this one, cleavage of this carbon hydrogen bond. So, you can write like this when you use Cl minus. So, you will lose so which can convert into the salt. Once you form the salt, when you do the hydrolysis, it can convert into aldehyde as a product. So, all of you know very well, if you have the imine, so you generate ammonium chloride as byproduct. So, in place of carbon monoxide, you can use hydrogen cyanide. In this case, you can see here you generate the hydrogen cyanide in the reaction medium, which can react with hydrochloric acid. You form this iminium ion as a product. Once you form the nitrile ion as a product, once you form this one, which can now act as electrophile, which can undergo reaction with this aromatic system to give you imine intermediate. This can convert into the salt, imine salt. Once you form this one, which can undergo hydrolysis to give the aldehyde as the product. Here another example shown here, and if you compare the Gattermann-Koch reaction and this one, where we have seen that you cannot use phenol as a substrate, because it can, like phenol or aniline, they can readily undergo reaction with Lewis acid. You do not get the formulation product. Under these conditions, you can use the hydroxy compound. For example, this orsinol can readily undergo reaction to give this aldehyde as the product. The presence of this reaction has been, as you can see here, has been carried out using the combination of zinc cyanide and hydrochloric acid in the presence of aluminum chloride at 0 degrees Celsius. The imine salt, whichever you generate, can be hydrolyzed using water to give this aldehyde as a product. Another example shown here, you can see this substrate having 2 hydroxy group as well as the ester group can also readily undergo formulation using the combination of zinc cyanide and hydrochloric acid in the presence of aluminum chloride to give this aldehyde as the compound. Just we have seen 2 examples for the formulation reactions. First one involves the combination of carbon monoxide and hydrochloric acid in the presence of Lewis acid, and the second example involves the combination of hydrogen cyanide, hydrochloric acid in the presence of Lewis acid. Now, let us look at here, and here also so the reaction acylation reaction shown in this case, and in the place of hydrogen cyanide, the acetonitrile has been used. This also can readily undergo reaction if we have the polyhydric phenols, which can readily undergo reaction with acetonitrile in the presence of zinc chloride hydrochloric acid to give the imine intermediate. Once you have this one, which can readily undergo hydrolysis to give this carbonyl compound. Now, let us see the mechanism. As you can see, the acetonitrile makes chelation with the zinc chloride. Then this aromatic ring undergoes addition reaction with this nitrile to give this imine intermediate. Once you form this one, which can lose a proton to give this imine intermediate. Once we have this imine, which can undergo hydrolysis to give ketone as the product. So, if you compare all these reactions, the first one involves the combination of carbon monoxide and hydrochloric acid. The second example, the Caterman reaction, involves the hydrogen cyanide with hydrochloric acid and Lewis acid. This Hoesch acylation involves the reaction of acetonitrile with polyhydric phenols in the presence of zinc chloride and hydrochloric acid to give this ketone as the product. Here the Hoffman-Fischer synthesis is shown, where you can see here the aromatic ring can readily undergo a reaction with this trichloroacetonitrile. In the presence of acid, it can give the ketone as the product. On the other hand, the base, it can be converted into the corresponding nitrile as the product. The mechanism of this transformation shown, this trichloroacetonitrile undergoes the presence of acid can give this salt. Once you form this salt, which can act as a electrophile under this condition, and this can readily undergo reaction with your aromatic ring to give this cation intermediate. Once you form the carbocation, which can lose a proton to give this nitrile, and this nitrile can react with hydrochloric acid to give the salt as the intermediate. Now, the imine salt depends upon the reaction conditions. If you have base, the base can remove the HCl and the presence of base, and you will be able to have this imine intermediate, which can further react with the hydroxide under these conditions. Then you can get the nitrile as the product as shown here. On the other hand, if you use acid hydrolysis, as we have seen earlier, you can convert in this imine into carbonyl group. Therefore, you can make this trichloroacetophenone as the product. So, if you compare all these reactions, the previous, if you look at the Hoesch reaction, where we have seen the reaction of acetonitrile, which can be readily reacted in the presence of Lewis acid and HCl to give acetophenone as the product. Here, and it is the reaction of trichloroacetonitrile shown in the presence of acid, as we have seen there, you can convert into the corresponding ketone as the product. On the other hand, the base, it can undergo elimination to give the benzonitrile as the product. Here some examples shown, and you can see this salt can readily undergo reaction with this polyhydric phenol derivatives, as you can see here, and it can undergo addition reaction, and you will be able to have this imine as the intermediate. Once you form this one, depends upon the reaction conditions, you can also try to further react with acid, you can convert into the corresponding ketone, and this also very useful intermediate. You can do further reactions to get useful compounds. And similarly, this example here, the reaction of this 2-methylthiophene is shown. This also can readily undergo reaction with this salt to give this addition product. So far, we have seen 4 examples. The first 2 example involves the formulation and then the acylation of aromatic systems using nitrile and trichloronitrile we have seen. Here the Vilsmeier formulation shown. If you look at this reaction, if you have aromatic system like having dimethyl amino substituent, those kind of substrate can readily undergo reaction with the dimethyl formamide in the presence of phosphorus oxychloride to give the corresponding aldehyde as a product. In this case, the formulation takes place at the para position. You can see here the yield is reasonably good. This reaction also works very well when you have this electron rich aromatic system. If you have the electron rich donating group, if you have the electron donating group, the reaction can be facilitated. The mechanism of this reaction shown here, dimethyl formamide, as you can, the lone pair undergoes this one, then it can undergoes addition reaction with this phosphorus chloride, you will have this intermediate. Once we have this one, now so this can undergo addition with this imine, and you will have this intermediate. Once you form this one, now this can lose, and you will be able to form this imine salt. This is known as Wills-Meyer reagent. This acts as electrophile in this reaction. Once if you have this one, now this aromatic ring can undergo reaction with this salt to give this additional product. Once you form this ammonium ion intermediate, which can now react the Cl minus and to give this intermediate, this can now lose, this can convert into this iminium ion, as you can see here. Once you form this one, when you do the hydrolysis with the water, and you will be able to form the corresponding aldehyde as the product. So, in the case of Wills-Meyer reaction, if you have electron donating group, the reaction is facilitated. For example, in this case you have the dimethyl amino substituent, which leads the formylation to give this para substituted aldehyde in 80% yield. However, this reactions is less effective when you have the simple aromatic ring like benzene, naphthalene, they do not undergo reaction. However, if you have the electron donating group, and if the system is electron rich, it can readily undergo the formylation with the Wills-Meyer reagent that can be readily generated from the phosphorus oxychloride and dimethyl formamide to give the corresponding iminium salt, which can readily undergo hydrolysis to give the aldehyde as the product. Here are some examples shown. Just I have shown the previous slide. If you have benzene and naphthalene, they do not undergo reaction. However, like anthracene, they can readily undergo reaction to give this aldehyde as a compound. Similarly, indole can undergo reaction at third position. You can introduce the formyl group, and similarly, if you have thiophene is electron rich, it can undergo reaction. You can get the 2 thiophene carbaldehyde as a product, and you can also, for example, this ketone also can undergo reaction, then you will be able to get this aldehyde as a product. The next example is Reimer-Tiemann formulation. As you can this, if you look at the previous reactions, so we have seen they usually form the iminium ion as electrophile, which undergoes reaction with the aromatic system to give the addition product, which leads to hydrolysis to give the aldehyde as the compound. If you see the previous example, which involves imine salt as electrophile, which undergoes reaction with the aromatic ring to give the substituted imine as a compound, which undergoes hydrolysis to give the aldehyde. But here, if you look at the phenol can be readily reacted with the chloroform in the presence of base to give salicylic as the product. So, this reaction also gives reasonable amount of (4-hydroxybenzaldehyde) as the byproduct. The mechanism of this reaction shown here. Base can now deprotonate this proton, then you will form this salt. Once you form the salt, now this can lose, convert into, so you will form the carbene. So, this carbene is electrophile, this reaction. So, in the presence of base, and this also can deprotonate the acidic proton, you have the phenoxide, which can readily undergo reaction with this carbene, dichlorocarbene, and you will be able to have this intermediate. Once you have this one, this can convert into this compound. Once if you have this one, when you react with substitution reaction, you will be able to have, when you react with potassium hydroxide, and you will be able to have this intermediate. Once you have this one, this can remove this proton, then comes out, then you will be able to form this 2-hydroxybenzaldehyde. And there is also, just as I have mentioned, there is also significant amount of 4-hydroxybenzaldehyde as a product in this reaction. So, this is one of the common method used to make salicylaldehyde. So, if you have the phenol can be readily react with the chloroform in the presence of base like potassium hydroxide to give the corresponding, you can introduce the aldehyde functional group at the ortho position, and in this way you can make formal salicylaldehyde in moderate yields. Here some examples are shown. So, if you have this dihydroxy compound, you can try to react with THP in the presence of acid, you can product one of the OH group. Now, you can try to selectively react with this hydroxy group. So, you can try to introduce the aldehyde functionality to the ortho position. In this way, you can make this compound, and similarly, you can also, for example, another here, this amino acid, the formulation of this amino acid shown here using chloroform and sodium hydroxide, you can try to introduce the aldehyde functional group at the ortho position. So, in this way you can try to selectively react chloroform in the presence of base, and you can convert into the corresponding carbene. Once you have the trichlorocarbene, you can react with the phenol derivatives at the ortho position, and which can be converted into the corresponding aldehyde as the product. The next reaction is Goldschmidt reaction. This, so far we have seen the examples, the first two examples, the Gattermann-Koch and Gattermann reactions and Vilsmeier, and the other reactions usually used for the Raymer-Diamond reaction we use for generally to make aldehyde as a product, and this example involves the reaction of phenol with the carbon dioxide in the presence of sodium hydroxide to give the carboxylic acid as the product. The previous reaction, if you look at it, the Raymer-Diamond reaction, where we have seen the reaction of phenol with the chloroform in the presence of base, and where you generate the carbene, dichlorocarbene as the reactive species which acts as electrophile, which undergoes reaction, you can readily convert phenol into salicylaldehyde. On the other hand, here you can look at in the place of chloroform use carbon dioxide, which can readily undergo reaction to give the salicylic acid as the product. This reaction has been carried out under heating. The mechanism of this transformation shown here. So, in the presence of base, as just we have seen, you form the phenoxide salt. Once we have the salt which can readily undergo reaction with this carbon dioxide as shown here, you have this addition product. Once you form this one, cleavage of this carbon hydrogen bond can lose proton, then you can get this carboxylate. Once we have this one, when you do the acid workup, you will be able to get the corresponding carboxylic acid, the product. So, in this way, if you have phenol, you can make salicylic acid using carbon dioxide in the presence of base. After acid workup, you can get the salicylic acid as the product. Here an example shown, the reaction of this dihydroxy compound shown, and this can be readily reacted with the carbon dioxide in the presence of potassium bicarbonate to give this carboxylic acid as a compound. Similarly, here the reaction of the phenol derivatives with the carbon dioxide in the presence of potassium carbonate shown, and you can introduce a carboxylic acid functional group at this ortho position to give this salicylic acid derivative. And here an example shown, and as just we have seen, Since this proton is acidic enough in the presence of base, you can deprotonate, you can form the phenoxide, which can readily undergo reaction with the carbon dioxide. In the presence of acid workup, you will be able to get the salicylic acid. Once we have this one, this in the presence of catalytic amount of acid can readily undergo reaction with acetic anhydride. You can make the aspirin as a product. As you can see here, which we often use for to treat pain as well as fever. So, aspirin usually can be made from salicylic acid with the acetic anhydride in the presence of catalytic amount of acid to give good yield. Here the Mannich reaction shown. As you can see here, and in this example, the reaction of indole with the formaldehyde and dimethylamine is shown here. In the presence of acid, it can give this. You can try to introduce alkyl amine substituent, and the mechanism of this reaction shown. In this reaction, first the aldehyde undergoes reaction with the amine. You form the iminium ion as a product which acts as electrophile. Once you form this iminium ion, which undergoes reaction with this aromatic ring, this, as you can see here, the third position, then you will be able to have this addition product. Once you have this addition product, that cleavage of this carbon hydrogen bond can give this derivative. You can see here, this is a very important example, and indole, in this way you can introduce the alkyl amine substituent through electrophilic aromatic substitution. The another example, the reaction of pyrrole is shown, which can readily undergo reaction with the formaldehyde and dimethylamine to give this derivative. In this also, the aldehyde first undergoes reaction with the aldehyde, you form the imine salt. Once you form the imine salt, which acts as electrophile as shown, this can undergo reaction with the pyrrole and you can get this compound. Similarly, this 2-methyl furan can readily undergo reaction with this iminium salt that can be generated with this dimethylamine and aldehyde to give this substituted compound as a product. This slide shows the reaction of electron rich aromatic system with the hexamethylene tetramine. In the presence of acid to give aldehyde. For example, in this case, a mixture of aldehydes can be obtained, and when you look at the ratio, the aldehyde that is formed with ortho position is always major comparing to that is generated from the para position. If you remember, already we have studied the formation of hexamethylene tetramine. If you have formaldehyde, which can readily undergo condensation with ammonia, we take 6 molecule of formaldehyde and 4 molecule of ammonia. So, they can undergo condensation reaction to give this hexamethylene tetramine. Already we have seen the formation of this compound. So, in this reaction, when you have electron donating group like OH or amino group, and this now readily can undergo reaction with hexamethylene tetramine in the presence of acid to give aldehyde, which is one of the practical synthetic route. If you want to make, for example, salicyl aldehyde, we can try to use this method. And in this reaction also, the iminium ion acts as a electrophile. Now, let me show the mechanism of this transformation, which is known as Stuff reaction. First, hexamethylene tetramine undergoes reaction with acid. For example, if you take acetic acid, the protonation of this nitrogen can give So, ammonium ion intermediate, once you form this one, this lone pair can push this, it can open up this carbon nitrogen bond to give an imine as intermediate. So, once you form this iminium ion, which can act as the electrophile, which can undergo reaction with for example, if you take phenol as substrate, which can undergo addition reaction with this iminium ion. When you react with, so when you protonate, you will be able to generate this acetate ion can deprotonate this one, then it can undergo addition reaction and you will be able to form so, this intermediate, once we form this one, this can convert into phenol derivative. So, once you form this one now, then you again can react with acid. So, protonation of this secondary amine can you form this salt. Once you form this one, so now this nitrogen lone pair can push this one, it can open up, you will be able to form NH2. Here you will be able to form iminium ion. This intermediate, once you form this one, now this can come here and then you will be able to form so this will be methyl group. You have here this one, then you are generating an iminium ion. So, once you form this one, now this can undergo reaction with, since you carry out the reaction aqueous acid. So, this can act as a nucleophile, can undergo addition with this iminium ion. You form this intermediate. Once the proton transfer can lead to the formation of we form this intermediate, this once we form this one, now can cleave this one to produce aldehyde plus so if you look at here, this is a crucial step. The hexamethyltetramine in the presence of acid and aqueous acid, it can undergo reaction to produce the iminium ion. Once we form the iminium ion, which can act as a electrophile, which can undergo addition reaction with this aromatic ring to give iminium ions product. Once we form this one, which can readily undergo hydrolysis, as we have seen in the previous examples, to give aldehyde as a product. This is one of the common reaction we use often to make salicylaldehyde. For example, if you have phenol, you can make salicylaldehyde in good yield and in the presence of aqueous acetic acid. This is commercially available. You can try to react when you heat, and you will be able to get the salicylaldehyde as a major compound. Now, let us look at some of the recent literature examples in this reaction. The first one, if you look at here, this substituted phenol can be readily reacted with the hexamethyltetramine in the presence of acetic acid and sulfuric acid to give this aldehyde as a product. This is one of the important aldehyde. If you look at this aldehyde, which is widely used to make silane ligand, two equivalent of this aldehyde can readily undergo condensation with diamine. For example, if you take cyclohexane diamine, when you mix them and stir it in alcohol solvent, you will be able to form this as a silane ligand. Once you form this one, when you react with metals like manganese acetate and cobalt acetate, so they can undergo complex formation. When you take this ligand and react with manganese acetate under air, it will be converted into for example, it will be oxidized under air. You will form the manganese 3 silane complex, which is first reported by Jacobson for the asymmetric epoxidation. For example, if you have styrene and the presence of oxidizing agent like iodosobenzene or sodium hypochlorite, you can try to oxidize. And so, this is used as a chiral ligand for the oxidation of alkenes, and this has been widely used around 1990. So, this aldehyde is popular one, is also commercially available. This aldehyde can be easily made from this substituted phenol using hexamethylene tetramine, and under these conditions, and once this aldehyde is widely used. I have shown one example here for the preparation of manganese saline complex, which is also used now for the preparation of cobalt saline and other chromium saline complex, which have been used for a variety of reactions. For example, chromium saline complex has been used for the Diels-Alder reaction. So, this is very popular aldehyde. This is usually made using the hexamethylene tetramine in good yield. The another example shown here, when you look at this compound, the polycyclic compound, and here also under using this combination of hexamethylene tetramine, trifluoroacetic acid, you can try to introduce aldehyde group in both the carbon atoms. In this case, in this substrate, a mixture of both aldehydes have been observed. Now, let us look at this example. Now, you have blocked this to ortho position and the para position is vacant. When you react with hexamethylene tetramine in the presence of aqueous sulfuric acid, you can try to introduce aldehyde group here. So, this is one of the practical method often we use if you want to make salicylaldehyde and or if you want to introduce aldehyde functional group in the aromatic ring, you can try to use hexamethylene tetramine, which is also very easy to make. Just as I mentioned, if you have formaldehyde, ammonia, if you react, then you will be able to form this. This is also commercially available. You can buy once if you react with this electron rich aromatic system in the presence of aqueous acid, you will be able to introduce the aldehyde functional group. Now, let us look at another example, the reaction of aryl magnesium halide or aryl lithium is shown. You can try to react with dimethyl formamide. This way, you will be able to introduce aldehyde functional group here. So, already we have seen when we studied the organolithium reagents. So, this also common method if you want to introduce aldehyde functional group. If you have, for example, bromobenzene, so you can react with magnesium, you can make, or you can try to react with the lithium, for example, n-beta lithium. So, halogen metal exchange, and then you will be able to form or you can also try to react with metal. Anyway, once you make the phenyl lithium reagent, this can be readily now reacted with dimethyl formamide, you will be able to introduce. And if you look at the reaction pathway, already we have seen when we studied the organolithium reagents. Let us take this one. Once if you have the phenyl lithium, if you have the dimethyl formamide, so which can undergo addition reaction, then you will be able to form this intermediate. Once you have this one, when you do the workup, then you will be able to transform this into so once you form this one, it can leave, then you will be able to get the aldehyde. So, now here an example shown. For example, if you have this aryl halide, you can try to react with the dimethyl formamide in the presence of, first what happens here, the n-beta lithium reacts with this aryl halide by halogen metal exchange, you will be able to make the corresponding lithium reagent. Once you form this one, as just we have seen, it can undergo addition reaction with this dimethyl formamide, you will be able to have this addition product. So, when you do the workup, then you will be able to get the aldehyde as the product. Professor Cummins made some modification to this reaction. Once you react with, for example, you have the phenyl lithium react with the dimethyl formamide, you will be able to have this intermediate without doing workup. If you add another equivalent of beta lithium, As if you remember, in the case of phenylithium, we have seen the nitrogen can make chelation and you can introduce the ortholithiation. You can similar way you can make here introduce you can introduce lithium in the ortho position. Once we have this one, now you can try to react with the electrophile as we have seen. Then following that, when you do the workup in this way, you can get this aldehyde which contains substitution in the ortho position. Here another example shown, and in this case, as just we have seen, you can try to react with the n-butyl lithium, you can make the corresponding so when you react with one equivalent of lithium, n-butyl lithium, you can make this one. Then as just we have seen, when you react with dimethyl formamide, so it can undergo addition reaction. So which in the presence of aqueous workup, so when you carry out the workup, this will be converted into this aldehyde. So this is also one of the common method we use to make aldehyde. For example, if we have the anisole, you can try to react with the n-butyl lithium. So you can convert into this. So when you add DMF, you will have so when you do the acid workup, and you will be able to get the corresponding aldehyde. So far whatever we have seen all are intermolecular reaction. Now let us look at this amide. When you have this amide which can undergo intramolecular cyclization in the presence of phosphorus pentoxide or POCl3 to give this isoquinoline derivative. This is also an example for electrophilic aromatic substitution reaction. For example, when you take this amide and when you react with POCl3 or phosphorus pentoxide, it undergoes reaction to give this isoquinoline derivative. So when you look at the reaction pathway, for example, if you take the phosphorus pentoxide, so once we have this intermediate, it can act as an electrophile. Now, this can undergo addition reaction. you have this intermediate. Once we have this one, this can lose proton. Since you have the PO3 minus, it can remove this proton. You will be able to have once you form this one, then lone pair can push this one, then you will be able to you will have this intermediate. This can lose this proton to give this derivative. Once we have this one, now this also can react the phosphorus pentoxide or POCl3. For example, let us take this one, and when you have this you have this intermediate. Once we have this one, this can now remove this proton, then you will be able to get the isoquinoline derivative. So, in this way you will be able to form the isoquinoline. Suppose if you have this amide which is bonded with this aromatic system, you can try to cyclize intramolecularly in the presence of phosphorus pentoxide and POCl3. Similar way you can try to draw the mechanism. So, you can get this isoquinoline derivative. In summary, in this class we have seen the formylation reactions. First we have seen the Caterman-Koch formylation, where we have seen the use of carbon monoxide in the presence of hydrochloric acid and aluminum chloride, where you have the acylium cation as the electrophile, which undergoes addition followed by elimination reaction. In this way you can convert into aromatic system into the corresponding aldehyde. Then we have seen the Caterman formulation. Here the difference, instead of in the place of carbon monoxide, here we use a Hessian, and where you form the nitroleum cation, which undergoes addition reaction to give the imine derivative. When you do the hydrolysis, you will be able to get the aromatic aldehyde. Then we have seen the Hoy's acylation, where in the place of Hessian they have used acetonitrile, hydrochloric acid or Lewis acid. You can try to introduce the aldehyde functional group. Here it depends upon the reaction conditions. Suppose if you use acidic condition, you will get the aldehyde. On the other hand, if you use the basic condition, it can undergo elimination to give the nitrile as the product. Then we have seen the Wills-Meyer formylation, where as just we have seen, and the dimethyl formamide undergoes reaction with the POCl3, and you are going to make Wills-Meyer reagent, which is an iminium cation which acts as electrophile, which can undergo addition reaction. When you do the workup, you will be able to get the aromatic aldehyde. Then we have seen the Reimer-Tiemann formylation. In this reaction, if you have the phenol in the presence of base, and it can react with the chloroform to give salicylate, for example, as a major compound. First the base reacts with the chloroform to give the dichlorocarbene as the electrophile, which undergoes reaction with the phenoxide that you generate phenol, and then when you do the workup, you will be able to get salicylaldehyde, which is also important precursor to construct variety of compounds. For example, when we often use to make Schiff base with amine, we use as a ligand to make inorganic complexes for the catalysis. Then we have seen the Goldschmidt carboxylation in place of, suppose if you take the phenol and base and carbon dioxide, you will be able to get salicylic acid as the product. This is precursor for the aspirin synthesis. We have seen when you have this one, when you react with acetic anhydride in the presence of catalytic amino acid, you can make the aspirin as the product. Then we have seen the Mannich reaction. Here the formaldehyde undergoes reaction with amine to make the iminium ion, which acts as electrophile, which can readily undergo reaction with the aromatic system. In this way, you will be able to make alkyl amine. You can try to introduce alkyl amine functional group in the aromatic ring. Then we have seen the tough reaction, where if you have electron rich system like phenol, which can readily undergo reaction with hexamethylene tetramine, which is produced from formaldehyde and ammonia. In the presence of aqueous acid, you can try to make salicylaldehyde. If you take phenol, where also iminium ion acts as an electrophile. Then we have seen this Powiat reaction, where if you have the aryl lithium, for example phenyllithium, which can readily undergo reaction with dimethyl formamide to give the addition product. Once you have this one, when you do the aqueous workup, it can convert into aldehyde. Then we have seen the pectate CAMS isoquinoline synthesis. If you have amide, which can undergo intramolecularly cyclization to give the isoquinoline as a product. So, if you look at these are some of the common reactions often we use to make aldehydes and the derivatives. For example, these are the reactions often used in the laboratory to prepare the aldehydes and milder reaction conditions in gram scale synthesis. With this, we conclude this lecture. Thank you very much.